Calculus with parametric curves. Back in differential calculus, you study the derivative, the first derivative, the second derivative of a rectangular function, right? The rectangular function I am referring to, let's say, for example, y equals to x squared. So that is a parabola. And then you study the derivative of a parabola. So you take the derivative of x squared, you have a 2x. The 2x, I should say y prime or f prime of x equals to 2x. This is one function that represents the slope of the parabola at an x value. And then if you want to look for the slope of the parabola at some specific point, let's say when x is equals to 1, you plug in 1 to the derivative, you have a 2. So the 2 is the slope of the parabola when x is equals to 1. So now you have a slope. When x is equals to 1, y is equals to 1, you have a slope, you have a point. You can use the slope and the point to build an equation of the tangent line, tangent to the parabola at that specific point. And we can do all of this to a parametric equation. So for parametric equation, I have x in terms of t and then y in terms of t. So we can say x equals to f of t and then y equals to g of t. So how about we start from the slope? So okay, let's say we find the slope of parametric curve. Okay, so for the slope, let's put the slope in red. So I will just write the formula in red. So put the slope in red. So find the slope of the parametric curve at point x comma y. X comma y. And then the first derivative, we need to do 1 for x, 1 for y, because they are each of this is in terms of t. So the first derivative of x, so that refers to x prime equals to f prime of t, that is equals to dx dt. And then first derivative, again, for y, of y, so that is y prime, which is g prime of t, that is equals to the derivative of y with respect to t. All right, then how about dy dx? So when you have a dy dx, so that will be the derivative of y with respect to x. So that is equals to, I need to split this up to a dy, the derivative of y with respect to t. How about this? To make this easier to read, I will put this using a different color. So how about this? dy and then let's use a different color for that. How about dy dt? And then the x is the derivative of x with respect to t. I will put the dt in a different color. And then you can see the dt, the over dt, the dt got cancelled. Then you go back to dy dx. And then since we have a denominator, we have to make sure that the derivative of x with respect to t is not equal to 0. Okay, then now we know that is the derivative. So how about we just put this on the parametric equation? Okay, then let me pick a parametric equation. So given parametric equation, so given parametric equation, and then let's do a x equals to square root of t, and then y equals to 1 over 4, t squared minus 4, and then provided t must be greater than or equal to 0. Let's move that up. And then how about we sketch the graph first? It is not going to take a long time to sketch the graph. I'm going to build a table. And then we have a table. So that line should be long enough. And then x equals to 0, t equals to 0, 1, 2, and 4. Let's try this. 0, 1, 2, and 4. And then we draw a line, and then we have x. So that is just a square root of 0, square root of 1, square root of 2, square root of 4. And then this is equals to 2. This is a 1. This is a 0. This is around 1.4. I just round. And then y is you have a 1 over 4, 0 square minus 4. And then 1 over 4, 1 square minus 4, 1 over 4. 2 square minus 4, 1 over 4, 4 squared minus 4 equal, and then the first one you have a negative 1, and then this is a negative 3 over 4, and then this is a 0, and then this is 16 minus 4 is 12, 12 divided by 4 is 3, and then we draw the point x comma y, this is a 0, negative 1, this is a 1, negative 0.75, this is a 1.40, and then this is a 2 comma 3, and then using this point we can sketch the parametric curve, and then let's build an xy plane. So that one, I will say this should be enough of space, right? So x goes from 0 to like a 2, so 0 and then 1 and then 2, and then this is y goes from a negative 1 up to a 3, so I will do a 1, negative 1, 0, 1, 2 and 3. Y-axis, x-axis, you don't see the t because t is a parameter. And then the first point, t must be in ascending order or increasing order. 0, negative 1. Again, and then 1, negative 0.75, around there. And then 1.4 comma 0. And then 2 comma 3 all the way up here, 2 comma 3. And then we connect them. So that one looks like a parabola. Okay, I'm going to make the curve look smoother. Okay, that will just keep going up like that. And then we draw the orientation. So orientation going up in this way. That is just like the direction. Okay, we just introduced parametric equation and then the derivative, but we haven't done any derivative yet. Okay, let's do some derivative. Okay, let's do a point. How about the slope? Can you tell me the slope at point? Let's do a 2 comma 3. 2 comma 3. This point, right here. This is 2 comma 3. At that point, so what is the slope? Okay, then we need to do a dx dt and then a dy dt. Okay, let's do it. Dx dt. So dx dt, that is equals to 1/2. So I bring square root is half power. I'm looking at this. Square root is half power. You take the derivative, that is a power rule. You bring the half power up front, and then you take the half power minus 1. I will just put this on my paper. 1/2 minus 1. And then this is equals to 1/2. And then t to the negative 1/2. That is 1 over 2 root t. Okay, we got the dx dt. And then we have the dy dt. That is equals to the y. Okay, the 1 over 4, we can ignore that. And then the derivative of t squared is 2t. I am looking at right here. The derivative of t squared is 2t. The derivative of 4 is 0. Minus 0. And then that is equals to 1/2 t. Okay, we got the derivative. And then a dy dx. That is equals to dy dt over dx dt. Okay, dy dt, we got that. That is a 1/2 t. 1/2 t. And then dx dt, how about I put 1 over 2, 1 over root t. So I can see that the 1/2 got cancelled. And then this is the 1 over root t. That will be a t times square root of t. So that will be the first power plus the 1/2. So that is equals to 3 over 2. That is equals to 3 over 2. And then my dy dx is equals to, t to the 3 over 2, or I would say the square root, and then t to the third power. And then this is the derivative of the parametric curve at t, when t is greater than 0. I cannot say at any t. It must be t greater than or equal to 0. When t is greater than or equal to 0, I have one derivative or one function that represents the equation that represents the slope of the curve. And then this is just a general derivative, so we have to emphasize that t is greater than or equal to 0. And then at this point, so this point is 2 comma 3, that is x comma y. Okay, at this point 2 comma 3, what is t equals to? That one, t is equals to 4. Okay, t is equals to 4. Let's use the green. Okay, t is equals to 4. We take this one from the green table. When t is equals to 4, you know what? The dx dt, so this one I like to do some names, because in differential calculus, every time I got a result, I prefer to do some names, okay, instead of just say that is the derivative. Okay, let's do a dy dx. We will come back to the t over 4. dy dx, that is equal to the square root of t to the third power. This is slope of parametric curve. Parametric curve means plane curve. They usually use a big C to represent that at t, where t is greater than or equal to 0. And then you have this point, and then you have a t, and then the slope is equals to dy dx, that is equal to the square root of, I would do a 4, okay, let's put the 4 in green, okay, if that is what you like. And then this is the square root of 4, 4, 4, 4, right? 4, 4, 4. The square root of each 4 is 2. 2 times 2 times 2 is 8. So that is equals to 8. Box that, and then you need to tell me what that is. That is slope of parametric curve. At 2 comma 3. Slope of parametric curve at 2 comma 3. And then what else can we do? In calculus, after we found the slope, we have a point, we can build a tangent line. Okay, slope is now equals to 8 at this specific point, not every single point. And then the point is 2 comma 3. We can find the tangent line. Find the tangent line. Tangent line is a straight line. Okay, tangent line is a straight line. Then what is the formula? The formula is point slope form of a straight line. Y minus y1 equals to slope times x minus x1. This is called a point slope form of a straight line. Point slope form. Okay, and then we do y minus y1, y minus 3 equals to 8 times x minus 2. And then we will just have to simplify that. You will get the slope-intercept form. And then y is equals to ax minus 16, and then you add 3 to it. You have y equals to ax minus 13, and then this is a slope-intercept form. Slope-intercept form. And then what is this? I said tangent line, right? So that is equation of the tangent line. To the parametric curve. Tangent to the parametric curve. At that point. 2 comma 3. So at this point, we just walk through the basic of derivative in differential calculus. So we got a function. They give you a point. The point is on the curve of the function, and then they ask you to find the slope, and then they ask you to find the tangent line. We just do the same thing on a parametric curve. Okay, let's draw the curve. We have the tangent line, right? Okay, for the curve, I will just, for my convenience, I will just go back and copy and paste that. Let me try to get the whole picture. Okay, copy and then paste. I want to sketch the graph of the tangent line. So we have a parametric curve. We have a point ax minus 13. So we know that the slope is equals to 8. That is a passive slope. Then the line is going uphill. And then we know the line should look something like this. So that is pretty steep for a passive slope. Okay, let's make that closer. So this is tangent line. y equals to ax minus 13. If you give me another point, any point on this green parametric curve, then that would be another tangent line because it has a different slope. And then one thing that we can quickly see is at this point, the slope is less steeper, right? So that will be a different tangent line and it has a different slope. And then how about this? We will just end the videos right there. So that is a good introduction. And then in the next video, I will do a horizontal tangent line. How's that? That is also what you study back in differential calculus. Okay, then we finish the video right there. I will start another video and then I will do a quickly recap from this video. All right, I will see you there.